Hey guys, I'm Jay. Today is my LeetCode review vlog on 114th problem, flatten binary tree to a linked list. We are given the root of a binary tree. We have to flatten the tree into a linked list. The linked list should use the same tree node class where the right child pointer points to the next node in the list, and the left child pointer is always null. The linked list should be the same order as a pre-order traversal of the binary tree. Let's see example 1 here to understand it easily. We got input binary tree here, and its pre-order traversal is 1, 2, 3, 4, 5, 6. And the linked list after transformation is also 1, 2, 3, 4, 5, 6. And also, the right child pointer points to the next node in the list, and left child pointer of each node is always null. Then, let's get started of the intuition to solve the problem. And the main idea to solve this problem are made of two steps. And the first step, we have to understand the pre-order traversal, which means that for every node in the binary tree, we first process the current node, then the left subtree, and finally the right subtree. Pre-order traversal. And the second step is, during the flattening process, the left subtree should be flattened and connected to the right of the current node, and the original right subtree should be moved to the end of the flattened left subtree. Then, let's get started by 3 different approaches to solve the problem. And the first approach is called recursive pre-order traversal. And we can recursively flatten the binary tree by first flattening the left and right subtree, and move the flattened left subtree to the right of the current node, and attach the original right subtree at the end of the flattened left subtree. Next, let's get started with the code of the recursive pre-order traversal to solve the problem. So the very first step, we have to handle a bad case. If the root node is null, we just return. Return. Next, we'll recursively flatten the left subtree and then the right subtree. Flatten root.left subtree. And then flatten right subtree. Next, after the recursion, we'll store the original right subtree because we'll overwrite root.right when moving the right subtree to the right. Tree node right subtree equals root.right. Next, if there is a left subtree, we need to move it to the right. And code is if root.left is not equal to null. Next, we'll move the left subtree to the right. And code is root.right equals root.left. So the root.right is overridden. And we'll set the left to null as the problem required. And the code is root.left equals null. Then we'll found the rightmost node of the newly moved subtree, so we can just attach the original right subtree to it. Tree node current, and the current node was started at root.right, and we'll create a while loop to found the rightmost node of the newly moved subtree. Current while current.right is not equal to null, we'll continue to find the rightmost node. Current equals current dot right. And out of the while loop, we'll attach the original right subtree to the rightmost node of the new right subtree. Current dot right equals right subtree. And that's all of the code. Let's submit code and check for the correctness. Oops, flatten. I spelled it wrong. Let me revise it and resubmit it again. Yes, our code got accepted. Then let's analyze the time and space complexity of the recursive pre-order traversal approach. For time complexity, each node is visited exactly one time, and for each node, we traverse through its right subtree to find the rightmost node. Therefore, the overall time complexity, it is big O of n. And for the space complexity, the recursion depth can go up to the height of the tree. And in worst case, the height of the binary tree can be n. For example, if the tree is a skewed tree. So the space complexity, it is also big O of n due to the recursive call stack. And this is the first approach. Next, let's get started by the second approach, which is called iterative pre-order traversal with a stack. Iterative pre-order traversal with a stack. Oops, with a stack. And for the second approach, we'll use an iterative method, and we'll need an extra stack to simulate the pre-order traversal. First, we'll perform a pre-order traversal using a Java stack. Next, we'll manually attach each node as we would in a linked list way, and set the left child to null and connecting the right child. Then, let's get started with our code. And the very first state is also the same. If the root is null, we just return. Then, we have to create a stack to store the nodes during the traversal to simulate the pre-order traversal. Stack of tree node. And let's call it stack and assign a new empty stack to it. Next, we have to push the root nodes into the stack. Stack push root node. And then we'll create a while loop, and if the stack is not empty, we'll continue the while loop. And inside while loop, first we'll pop up the top node from the stack. Tree node current node equals stack dot pop. Next, we have to push the right and left children, which we can also call it right and left subtree, to the stack. But we'll push the right subtree first, so it will be processed after left subtree. If current node dot right is not equal to null, then we'll use a stack dot push, and the parameter is current node dot right. And it's very similar for the left subtree. Current node dot left is not equal to null. Then we'll push it. Stack dot push current node dot left. So the left subtree would be at the top of the stack. Next, we have to check if the stack is now empty. If so, the next node in the pre-order traversal should be the top node of the stack. If stack is node is empty. If stack is not empty, we'll get the top node from the stack. So current node dot right equals stack dot peak. Next, we'll set the left child to null as the problem required. Current dot left equals null. And that's all of the code for the second approach, iterative pre-order traversal with a stack. Oops, we have to finish is current node is the current node. Yes, our code got accepted. Then let's analyze the time and space complexity of the second approach. For the time complexity, we visit every node exactly one time, and every node is pushed and popped from the stack once. Therefore, the overall time complexity, it is big O of n. And for the space complexity, in the worst case, the stack would contain all the tree nodes in the tree. So, in the worst case scenario, a complexity unbalanced tree. So the space complexity, it is also big O of n. And then let's start it with the third approach, which is called Morris traversal. So for the third approach, Morris traversal, and the detail is we'll modify the binary tree in a way that we use the left subtree as a thread to traverse without using extra space for recursion or a stack. So we don't need any extra space. Then let's get started. First, we'll traverse tree without extra space by using a pointer called current. Tree node current equals root, starting at root. Next, we'll create a while loop to check if current is not equal to null. We'll continue the while loop. And inside while loop, for each node, if the left subtree exists, we'll found the rightmost node of the left subtree first. If current dot left is not equal to null, then we'll found the rightmost node of the left subtree. Tree node predecessor. Tree node predecessor equals current dot left. Then we'll create a while loop to find the rightmost node. Predecessor dot right is not equal to null. Then we'll make the predecessor points to the right node of predecessor. Predecessor equals predecessor dot right until we found the rightmost node. Then we'll connect the original right subtree of the current node to the rightmost node of the left subtree. Predecessor dot right equals current write. Then we'll move the left subtree to the right and set the left child to null. Current dot right is equal to current dot left. And we also have to set current dot left to null as the problem required. And out of the if condition, we'll move to the next node. Current equals current dot right. And that's all the code for the Morris traversal approach. Let's submit code and check for the correctness. Yes, our code got accepted. And for the third approach, the time complexity is each node is visited twice. Once when we found the rightmost node, and the second time is during the main loop. So the overall time complexity is also big O of n. But the space complexity is very different. This is because the Morris approach didn't use a stack or recursion. So the space complexity, it is big O of 1, which is constant. And this is the end of my LeetCode review vlog on the Flatten Binary Tree to linked list problem. And I highly recommend you guys to visit my online GitHub page here, which contains all nodes for each LeetCode problems. For example, you can see the problem description, intuition, the idea, and detailed code, and time and space complexity analysis. By the way, you can also visit my GitHub repository here, which contains all the nodes and code of the docs file to build this online GitHub page. And thank you guys for your watching. And I'll put those two links on my YouTube description below. And this is the end. Thank you guys again, and see you next time. Bye bye.